Greetings. Today we're going to see a proof of Fubini's theorem. This is a theorem in multivariable calculus that allows to calculate double integrals. The double integral of a continuous function over a rectangle is equal to iterated integral, and we can calculate the iterated integral in either order. That is Fubini's theorem. Now, before we prove Fubini's theorem, let's recall how integration works in single variable. Suppose I have some function, this is y equals f of x, and that's the graph, and we're trying to integrate from a to b, and we're trying to find the area under the curve, and the way we do that is to slice it up into many rectangles. That's many rectangles right there. So we slice overall the distance between a and b is b minus a, and if we slice it into n rectangles, call that delta x, then we can sample these points. This first one is, let's say xi is equal to a plus I times delta x. So then this one would be x1, this would be x2, and so forth. And then we can evaluate these rectangles. Let's use right-handed rectangles for now. So then the area of those rectangles would be sum as I goes to 1 to n of f of xi. That's the height. We also want to multiply that by delta x to get the width. And then, so that's the area of each rectangle. We sum them up, and we take the limit as n goes to infinity. That's so that we have many rectangles. And then we don't actually want to calculate this limit, and we turn this into a Riemann sum from a to b of the function f of x dx. And notice what's happening in terms of notation is that we're dropping the sub i's because we're no longer sampling points, but rather we're treating f of x as a function, and delta x turns into dx, and we have an integral. Now let's come back to Fubini's theorem, and we need to set up a double integral. So let me draw a picture. Here's proof. Let's draw a picture x, y, z. Let's say x goes from a to b, and then y goes from c to d. That's the rectangle R right there. And then the double integral is defined where we slice it up into a lot of little pieces, and we'll slice it in both directions into many pieces. And then for each one, we can sample at one point and then get some kind of surface going up right there. Maybe the surface looks like that. That surface is z equals f of x comma y. And then, that's also subdivided according to the same subdivision from below. And then each one will consider some kind of rectangular box. So over each rectangle, we get a rectangular box. So as before, we need to set up some notation, and we can use the same thing. Delta x is b minus a over n. X sub I is a plus I delta x. So we're sampling the points here. A, so this would be x1, x2, and so forth. We also need to do the same thing in the y direction. Delta y equals d minus c over, let's use a different variable m, and then y, let me use a different variable, yj equals to c plus j times delta y. And then, so we also have various coordinates here. This is y1, this is y2, and so forth. And then we can also divide the rectangles in different widths, but I think the easiest is just use the same width for all of them. Then what we'll do is evaluate the function xi, evaluate the function f at xi, yj. That gives us a specific point and then the height of that rectangle. of that rectangular box. The volume. So right now we have some piece like this, where this point is x sub I, y sub j, and then if we evaluate it at f, then this point is x sub I, y sub j, f of x sub I, y sub j. That's the height of this rectangle. That's this thing. And then, sorry, I said rectangle again, that box. And then we want to get the volume of that box. So volume of one box is equal to f of x sub I, y sub j times delta x, delta y. Oh, that is the volume of one box. And then we would like to sum up all the boxes and then take the limit as before. So let's write this out. So then the total volume under the graph, that's the double integral r f of x comma y dA. This is defined to be limit as n goes to infinity and m goes to infinity. Now we want the number of subdivisions to be really, really, really big. And then we sum this up where we need two sums, f xi yj delta x delta y, and then that sum I goes from 1 to n, and then j goes from 1 to m. Sorry, my m looks horrible. Let me write it again. So that is the sum that we have. Now let's start massaging this. I would like to take the limit one at a time. So let's take the limit, leave the limit as n goes to infinity outside, and then take the limit as m goes to infinity. And then I would write these two sums as well. And one thing I'm going to fix is that this delta x and delta y, notice here this n has something to do with delta x, and this sum has something to do with the x direction. I'm going to deal with x later, right, outside. So let me also push this limit inside that sum. So we're currently assuming that everything is nice enough that all these operations work. So we're interchanging the order of these operations. All I've done is push this limit inside the sum, since m is n and m, they're different. Then let me put parentheses around here and here. And notice now this looks like a Riemann sum. To help us notice this thing, let's write this as equals limit as n goes to infinity for the sum I equals to 1 to n, and then let's call this entire function g of x, but we're evaluating at I, g of x sub I, delta x. So what is my definition for g? Well, with g of x equals to this whole thing, limit as m goes to infinity for the sum j equals 1 to m of f of x y sub j. Oh, I forgot the little tail here for j, delta y. So notice here I have x for g of x, and then we're evaluating that at x sub I to get the x sub I there. And then we can work on this in a moment, but let's finish this part. So remember, a limit of a sum of some function sampled at certain points is simply the integral of that function And now there's no sub I because we're thinking of this as a function. Dx is our notation, and x goes from A to B. Oh, that is our answer. Except we haven't worked out what g of x is, which we should do in a moment. So then here g of x is equal to limit as m goes to infinity. I'm copying it over because I ran out of room on the other sheet of paper. So let's work on this for a bit. Well, this is limit as m goes to infinity. Let's again write a function just to be careful. So we want a single variable function. How about h of yj delta y with h of y equals f of x comma y. So h is really just a single variable function that coming from f, thinking that x is a constant. Everything in here really depends on x, but I'm hiding that detail for now. And then we can see that this is our usual Riemann sum situation. And then notation-wise, we would write something like that. But really, what this was just to help us recognize that that is a Riemann sum. What it is integral from c to d of f of x comma y. Because all we're doing is just thinking of it as a single variable function. Right? So maybe we can note here, treat x as constant when we're trying to integrate this. And that is what this function is. Yeah, g of x, x is some number. It might be 23. And then here, this is just a single variable function in y, and we can integrate it. You already know how to do that in iterated integral situation. So in any case, we have this integral, and then that's g of x. So we can put that in there. That's what we were doing. We were calculating all of this, and we got here, and then we got sidetracked with calculating g of x. And apparently I can't show both of them here. I could do this here. So let's continue here. And this is equal to integral from a to b of g of x. And we figured out g of x is the integral from c to d of f of x comma y dy. So that's what we figured out over here. That's g of x, and we still have the dx outside. So that is our derivation for the volume under the graph, the double integral, as iterated integral, integrating y first, then x first. And so that's the end of the proof. Of course, if you wanted the integral in reverse order, then we would simply push these limits and interchange all the orders, and then we can do the same process again. That's the proof of Fubini's theorem for you. All right, bye.